So what we're going to work on now is proving quadrilaterals in the coordinate plane. So what do we have to do with this is we're going to take certain coordinate points that were given, connect them together, and then try to determine the type of quadrilateral or classify the quadrilateral based off of using the distance formula and slopes to help us to be able to do this. Okay, so let's go through an example together to do this. Now, I'm using a program called Desmos, and you can use that if you want to use an electronic way of graphing points and plotting them. Now, with the way that the points are written, you're going to want to go ahead and plot them and then label them and connect them together in that order that they are written. So here we know we have a quadrilateral, and it's A, B, C, D are going to be your vertices. And we need to determine which type of quadrilateral it could be from the ones that you've already learned. So let's go ahead and plot the points, connect them together, and see what we get. So to start with, we need to go ahead and plug in. It's 1, -2 is the first point. Then we have 7, -5, 4, -8, -2, -5. Now, what I'm going to do is I'm going to want to make sure everything is connected together. So I actually have to plot the point 1, -2 again on the diagram so that I can show you everything is connected. And there we go. So here's our quadrilateral that we have. Now we can kind of look at it and we get an idea, oh, well, it definitely doesn't look like a kite. But again, we can't make assumptions. So let's make sure that it is what we want it to be. So we can take this diagram and use that as our basis to start with. So here it is on the side. Now I'm going to go through and try to figure out the different lengths of the sides, but also I need to find the slopes to see which sides might be parallel to each other or even possibly perpendicular to each other. So if we start by first having all of the points again on here labeled A, B, C, and D, we can start off with AB first and find out what the distance is between A and B. So we find the length, but we can also find the slope of A and B. So let's start with the slope because we know that the slope, again, is going to be our change in y over change in x. And that one might be a little easier to get done and to get started. So first we're looking at A to B. So change in y is -5 minus a -2. And that is over 7 minus 1. So that will leave us with -5 plus 2 over 6, which is equal to -3 over 6, which reduces down to -1/2. So our slope here is -1/2, okay? So that's going to be our slope for AB. Again, we're first starting with AB, so it probably would be good that I make sure that I clarify this is for AB. Okay. Now let's find the distance between the points. So to find the distance between the points or find the length of AB, it's going to be equal to, again, the square root of the difference of your x's squared plus the difference of your y's squared. So in this case, our x's, we have 7 and 1. So 7 minus 1. And our y's is -5 minus -2. So square root of 6 squared plus -3 squared, square root of 36 plus 9 square root of 45. And if we simplify that down, square root of 45 is going to give us 3 square root 5. So AB is equal to 3 square root 5. Okay, so we know the slope and we know the length for AB. Okay, so here it is. AB is 3 square root 5, and the slope, remember lowercase m we use as a symbol for slope, is going to be negative 1/2. Now, if we're trying to see if this is possibly a parallelogram, we could go ahead right away and look for CD. But let's just take each side as it comes. So let's look at BC next and what we get there. Okay, so we'll go ahead and divide this up. And our next set would be BC. So if we go ahead again, same idea, change in y over the change in x. And then that's equal to, what do we have here? B to C. So negative 8 minus negative 5, so it becomes plus 5. Just put those in parentheses, you don't have to. And then we want to go ahead and look at 4 minus 7. So here we have negative 3 over negative 3, which is equal to 1. So the slope here is 1. And then we go ahead and find our distance. BC is equal to square root difference over x's. So notice that this is kind of easier because you kind of already do the difference when you find your slope, right? Not kind of, you actually do the difference when you find your slope. So it helps you when you're solving and using the distance formula now. And then 4 minus 7 is negative 3. That stays in parentheses. And you get a negative 3 over here as well. And you get the square root of 9 plus 9, which is the square root of 18, which ends up giving you 3 square root 2. So the length of BC is 3 square root 2, and the slope is 1. All right. Next. Let's continue with CD. Okay, the slope for CD, again, change in y, so negative 5 minus negative 8 is a plus 8 over change in x, which is negative 2 minus 4, which gives you negative 3 over negative 6. Sorry, that was positive 3 over negative 6. And that leaves you with negative 1/2. And for your distance, okay, negative 5 plus 8 squared plus negative 2 minus 4. Okay, square root of positive 3 squared plus negative 6 squared. You'll notice we basically did this earlier because you get 9 plus 36 again. saw that earlier, right? So square root of 45. And that's going to leave you with 3 square root 5. Okay, so CD is done. Okay, and the last one that we're going to do, go ahead and do from D to A. Okay, change in y, -5 minus -2 is going to give us a +2. And then -2 minus 1. So you end up with -3 over -3, which gives you 1. That's for your slope. And then for your distance, or the length of dA, same thing again, -5, it ends up being +2. But this time, once you do that, you're going to square it, and you're going to add that to the difference of the y's squared. And that's -3 squared plus -3 squared. Now you've seen this again somewhere, but we'll go ahead and finish it out. 9 plus 9 is equal to the square root of 18, which is equal to 3 square root 2. So dA is equal to that. All right, so now I wrote out all the slopes and I wrote out all of the lengths. So now we start comparing things. Okay, we start comparing, and if you notice, the ones that are opposite to each other, the opposite sides have both the same slopes. If they have the same slopes, remember they're parallel. So all opposite sides are parallel. You automatically know you have a parallelogram. The next thing you have to consider, though, is what about the side lengths? Well, the opposite sides are the same. So since not all of them are the same, we definitely know that we don't have a rhombus and we don't have a square. But what we do know is that the opposite sides are parallel and equal. So that tells us that we definitely have a parallelogram in this situation. Because if you look at some of the pieces of information that are in this diagram, that's the only thing that would actually work here. Because if it was a rhombus, then all of the angles would be equal. And that's not the situation here. And if it was a square, we would know all the angles would be equal. Everything would be the same. It would be perfect. Okay. And so if it was a rectangle or a square, you'd have 90-degree angles. So you'd also have that involved. And you don't have that in this situation. So we can conclude that in this particular diagram that we have a parallelogram. Notice I just put in the markings so that we can kind of put that there together. And you'll just have to always refer back to your table or your chart that has the properties. Use your foldable. It tells you specifically the details of these. Now, if you then start to have to deal with diagonals and figuring those out, you would just find the length or the distance between B and D and the distance between A and C. And then you could find your diagonal lengths. So it's once you apply the distance formula and the slopes, and once you gather the information you have, you'll be able to identify the type of polygon that you have there, or quadrilateral in this particular situation.